Hello and welcome to the AI Fundamentals course. My name is Andrew Conniff and I'm a Microsoft Technical Trainer or MTT with Microsoft. This course is divided into 5 sessions. Session 1 is the fundamentals of artificial intelligence. Session 2 is going to be the fundamentals of computer vision. And in session 3, we're going to talk about the fundamentals of natural language processing. In session 4, it's all about document intelligence and knowledge mining with Azure AI Search. And then we're going to wrap up with the fundamentals of generative AI. In our first session, we're going to create the foundation of knowledge in our AI. We're going to discuss how the AI models are created and the wide variety of tasks we can accomplish with them. And then we're going to discuss how we can access those tools in Azure and help us create our own AI models, and then how to rapidly add AI to our applications and solutions with the pre-built AI models. So let's get started. Our session is divided into 3 parts, or this part of our session, and it's the fundamental AI concepts, and then we're going to talk about the fundamentals of machine learning, and then the fundamentals of Azure AI services. In the first section, we're going to answer 3 big questions about AI. We start with what is AI? This gives us a baseline for the rest of the sessions. And then what are some common AI workloads and understanding where AI fits in the organization? And how do we add AI workloads in a responsible way? So here we're going to talk about the tools we use that guide us and help us be responsible in working with AI. Artificial intelligence is when machines, like computers, can do things like normally require human intelligence. Things that most humans do daily, often subconsciously. We make predictions, or we recognize patterns, and we use information that's available with our experience to guide us. We intuitively know when something isn't quite right or doesn't fit a pattern. Humans with vision use sight to experience the world visually, identifying options and written words around us. And we communicate by writing and speaking and engaging in dynamic conversations, responding appropriately. We can extract information from multiple sources to extend our knowledge. So here we're listing common workloads individually, but it's important to understand that we will often combine workload types and some will overlap with the capabilities, and that is expected. So for example, imagine a conversational AI solution that uses a chatbot to process an auto insurance claim. The bot relies on some natural language processing capabilities to make sense of input, such as I want to submit a claim, which can be typed or spoken. This chatbot may allow the user to send a photograph of the damaged vehicle and use computer vision to assess the damage and apply a machine learning model to predict likely repair costs. The bot might also use anomaly detection to identify potentially fraudulent claims. And finally, the claims data, including forms, photographs, and other artifacts, might be indexed to extract insights and create a searchable knowledge store to help manage future claims. At Microsoft, AI software development is guided by a set of 6 principles for responsible AI. Let's go through some scenarios that illustrate each of these principles of fairness. First, we'll start with fairness, which is an AI system should treat all people fairly. For example, suppose you create a machine learning model to support a loan approval application for a bank. The model should make predictions of whether the loan should be approved without incorporating any bias based on gender, ethnicity, or other factors that might result in an unfair advantage or disadvantage to specific groups of applicants. Azure Machine Learning includes the capability to interpret models and quantify the extent to which each feature of the data influences the model's prediction. This capability helps data scientists and developers identify and mitigate the bias in the model. Reliability and safety is another key concern. Our AI systems should perform reliably and safely. For example, consider an AI-based software system with an autonomous vehicle or a machine learning model that diagnoses patient symptoms and recommends prescriptions. Unreliability in these kinds of systems can result in substantial human risk and loss of life, potentially. AI-based software application development must be subject to rigorous testing and deployment managed processes, and that ensures that they work as expected before release. And privacy and security is obviously a huge concern. AI systems should be secure and respect privacy. The machine learning models on which AI systems are based rely on large volumes of data which may contain personal details that must be kept private. Even after the models are trained and the system is in production, it uses new data to make predictions or take action that may be subject to privacy or security concerns. Inclusiveness All AI systems should empower everyone to engage people and engage all people. So AI should bring benefits to all parts of society, regardless of physical ability, gender, sexual orientation, ethnicity, or other factors. And transparency, all of our AI systems should be understandable. Users should be made fully aware of the purpose of the system and how it works, what limitations may be expected. Finally, we have accountability. People should be accountable for AI systems. Designers, developers, and AI-based solutions should work within a framework of governance and organizational principles that ensure the solution meets ethical and legal standards that are clearly defined. In this next section, we will discuss how the AI models we use are created and what tools are available to create your own models. The fundamentals of machine learning is in 5 parts. What is machine learning? Types of machine learning, model training and validation, what is deep learning, and what is Azure machine learning. So machine learning can be described as some variation on the following 4 steps. The training data consists of past observations in most cases. The observations include the observed attributes or features of the thing being observed and the known value of the thing you want to train the model to predict, and that we call that the label. In mathematical terms, you'll often see the features referred to use the shorthand variable names x, and the label is referred to as y. Usually, an observation consists of multiple feature values, so x is actually a vector or an array of multiple values, such as x1, x2, x3, etc. An algorithm is applied to the data to try to determine a relationship between the features and the label, and generalize that relationship as a calculation that can be performed on x to calculate y. The specific algorithm used depends on the kind of predictive problems you're trying to solve, but the basic principles is to try to fit the data to the function in which the values of the features can be used to calculate the label. The result of the algorithm is a model that encapsulates the calculation derived from the algorithm as a function, and let's call it f. It's f for function. So mathematical notation, y equals the function of x. Now, the training phase is complete. The training model can be used for inferencing. The model is essentially a software program that encapsulates the function produced by the training process. You can input a set of feature values and receive as an output the prediction of the corresponding label. Because the output from the model is a prediction that was calculated by the function, it's not an observed value, and you'll often see the output from the function y hat as shown on the slide. Supervised machine learning is a general term for machine learning algorithms in which the training data includes both the feature values and the known label values. So supervised machine learning is used to train models by determining a relationship between the features and the labels in past observations, and then predict them for the future cases. So regression is a form of supervised machine learning in which the label predicted by the model is a numeric value. For example, the number of ice creams sold on a given day based on the temperature, rain, and wind speed. The selling price of a property based on its size in square feet, the number of bedrooms it contains, and socioeconomic metrics for its location. Or the fuel efficiency in miles per gallon of a car based on its engine size, weight, width, height, and length. Classification is a form of supervised machine learning in which the label represents a category or a class. There are 2 common classification scenarios. So binary classification, the label determines is the item there or is it not there, an instance of a specific class. So to put it another way, the models predict one of 2 mutually exclusive outcomes. For example, whether a patient is at risk for diabetes based on clinical metrics like weight, age, glucose level, etc. So they either are or they are not. Or whether a bank customer will default on a loan based on income, credit history, age, and other factors. Or if a mailing list customer will open a positively marketed item to their demographic based on their past purchases. In all of these examples, the model predicts a binary true or false, positive or negative, yes or no type of answer for a single possible class. Multi-class classification extends the binary classification to predict a label that represents one of multiple possible classes. So, for example, the species of a penguin, we have, a Delhi, Gentoo, or a chinstrap based on its physical measurements. the genre of a movie, comedy, horror, or romance, or science fiction based on the cast, the director, and the budget. In most scenarios, this involves a known set of multiple classes, and multi-class classification is used to predict mutually exclusive labels. So for example, a penguin can't both be a Gentoo and a Deli. However, there are also some algorithms that you can use to train multi-label classification models in which there may be more than one valid label for a single observation. So for example, a movie could potentially be categorized as both science fiction and a comedy. Unsupervised machine learning involves training models using data that consists only of the feature values. So there is no known labels. Unsupervised learning algorithms determine relationships between the features of the observations in the training data. Clustering is the most common form of unsupervised machine learning. A clustering algorithm identifies similarities between observations based on their features and groups them together in discrete clusters. So an example of that would be similar flowers based on their size, the number of leaves, the number of petals, or identifying a group of similar customers based on their demographic attributes and purchasing behavior. In some ways, clustering is similar to multi-class classification in that it categorizes observations into discrete groups. The difference is that when using the classification, you already know the classes in which the observation is belonging to. So the algorithm works by determining the relationships between the features and the known classification label. In clustering, there's no previously known cluster label. The algorithm groups the data on the observations purely on similarity features. In some cases, clustering is used to determine the set of classes that exist before training a classification model. So for example, you might use clustering to segment your customers into groups and then analyze those groups and identify the categories of different classes. So high value, low volume, frequent small purchaser, that type of thing. You could then use your categorizations to label the observations in your clustering results and use that labeling data to train classified models that predicts to which customer category a new customer might belong. Now let's relate this to X and Y from the previous slide. In the ice cream sales scenario, our goal is to train a model that can predict the number of ice cream sales based on the weather. So the weather measurements for the day, temperature, rainfall, wind speed, and so on, would be in the features X, and the ice cream sold on each day would be the label Y. In the medical scenario, the goal is to predict if a patient is at risk of diabetes based on their clinical measurements. The patient's measurements, weight, blood glucose, etc., are the X, and the likelihood of diabetes would be example 1 or 0, or no risk would be the label Y. In the Antarctic research scenario, we want to predict the species of a penguin based on its physical attributes. The key measurements, the length of the flippers, width of the bill, and so on, are the features X, and the species, for example, Adele or Gentoo, would be the label Y. Training is the heart of machine learning. It's where we teach the model to find the patterns in the data. We use an algorithm to adjust the model until the data fits as well as possible. After training, we have the model that we can test. So we use some of the data that we set aside at the beginning, and we call that data validation data. That's to test how close our model's prediction labels are to the actual labels. In the case of unsupervised learning, where we don't know the actual labels, we measure how well the model's prediction are predicted on the labels. So we're separating clusters. There are many types of evaluation metrics. The important thing to remember is that the goal of machine learning is to find a model that gets as close as possible to predicting the actual label. The best model can still have a margin of error. Deep learning is an advanced form of machine learning. It tries to emulate the way the human brain learns. The key to deep learning is that the creation of an artificial neural network. And this simulates the electrochemical activity in a biological neurons by using mathematical functions. So the artificial neural networks are made up of multiple layers of neurons, especially defining a deep nested function. So this architecture is the reason the technique is referred to as deep learning, and the models produced by it are often referred to as deep neural networks, or DNNs. You can use deep neural networks for many kinds of machine learning problems, including regression and classification, as well as more specialized models for natural language processing and computer vision. To better understand how deep neural network models work, let's explore an example in which a neural network is used to define a classification model for penguin species. So the feature data X consists of some measurements of a penguin. Specifically, the measurements are the length of the penguin's bill, the depth of the penguin's bill, the length of the penguin's flippers, the penguin's weight. And the label we're trying to predict, Y, is the species of that penguin. And there are 3 possible species it could be: Delhi, Gentoo, or Chinstrap. The process for inferencing a predicted penguin class using this network is the feature vector for a penguin observation is fed into the input layer of the neural network, which consists of a neuron for each x value. So remember, those are the input values. So in this following example, the x vector is used for the input. They're showing like 37.3, 16.8, etc. The function for the first layer of neurons each calculate a weighted sum by combining the x and the w, the weight. So each neuron in a layer is connected to all of the neurons in the next layer. The results of each layer are fed forward through the network until they reach the output layer. The output layer produces a vector of values, in this case using a softmax or similar function, to calculate the probability distribution for the 3 possible classes of penguin. In this output vector is 0.2, 0.7, and 0.1. The elements of the vector represent the probabilities for classes 0, 1, and 2, our 3 penguin types. The second value is the highest, so the model predicts that the species of the penguin 1 is Gen 2 in this case. The model learns the appropriate weights by iteratively passing the training data through and evaluating the predicted probabilities for each class against the known class label. So the weights are adjusted in each iteration to reduce the amount of error or loss between predicted probabilities. For example, the 0.2, 0.7, 0.1, and the values that represent the actual class label, for example, 0.0, 1.0, and 0.0 for class 1 Gen 2. Microsoft Azure Machine Learning is a cloud service for training and deploying managed machine learning models. It's designed to be used by data scientists, software engineers, DevOps professionals, and others to manage the end-to-end lifecycle of machine learning projects, including exploring data and preparing it for modeling, training and evaluating the machine learning models, registering and managing trained models, and deploying trained models for use by applications and services. Reviewing and applying responsible AI principles and practices. Once you've provisioned an Azure Machine Learning workspace, you can use it in Azure Machine Learning Studio, a browser-based portal for managing your machine learning resources and jobs. And in that Machine Learning Studio, you can, among other things, do the following. You can import and export data. You can create and use compute resources. You can run code in notebooks. You can use visual tools to create jobs and pipelines. You can also use automated machine learning to train models, view the details of those trained models, including the evaluation metrics, the responsible AI information, and training parameters. You can also deploy the trained models on request and use batch inferencing. You can import and manage models from a comprehensive model catalog as well. In this demo, you will see how machine learning features can be used to train a machine learning model and to make predictions. Here we are in Azure, and I'm creating an Azure machine learning resource. I'm going to put it in my resource group, which is going to act as a lifecycle container for all of the things that I need for my tool. I'm going to go ahead and set my configuration, and then I'm going to do a validation and create step here. All right, there's my machine learning resource. And what I want to do is launch the studio. This is where the machine learning work is going to take place. And so we're going to do an automated machine learning step here, and we're going to do a regression count. So we're going to go ahead and create a new job, and we're going to fill out some configuration before we get to see what's going on. So we're going to give our job a name, and then we're going to set up our experiment name and our description. So as you go through here, you can go through, you can see the different configurations that you can create here. We're going to choose regression to get different results, or to, depending on what your data requires, to set things up. All right, so we're going to create a data asset. We're going to give it a name and a short description. All right, this is going to be our bike rental data. And I'm going to then get this and choose the correct one that I want. And we're going to approve our data set. And there's the path that we do for the upload, and we're going to go ahead and upload from folder now. So we're going to find our bike data, upload all of it, and give that a minute to do that. All right, looks like it's done. There we have our data. We're going to go next. So we've imported the data. We've connected it to our job. All right, we're going to make a couple settings here. So we're going to go ahead and we're going to choose the random forest and the light GBM. There we go. So there's different models for our base that we can use, and we're going to go ahead and set some other configurations here. The important thing is that you can see how powerful the tool is and how much control we have over each of our data imports and the variety of ways that we can choose different base models and then choose different fine tunings. All right, we have everything set up. The status is complete. We've done our data ingestion. We're going to go through it and we can see our details of what's happening. If we go to our metrics, we can see our predicted tree and our histogram there. Okay, so now we want to deploy the model. So we've gone through, we've trained it, our data's in there, we've given on our parameters, it should give us now a nice regression number. So that regression was on that the prediction tree. It should follow along that line. We're going to go ahead and deploy our model to an endpoint, and now we're going to go to that endpoint and see what's there. So we have our endpoint, it's succeeded. We're going to test it now. And to do that, we're going to put in some categories that work with our data. And there we go. We have a nice regression that falls on our line. And it's just that easy to test it and make it available. That's been a quick tour of Azure Machine Learning. The fundamentals of Azure AI Service section is in 3 parts. Azure Basics, a brief introduction to Microsoft Azure. AI services available on Microsoft Azure, and Azure AI services. Microsoft Azure is a hyperscale cloud service, and what that means is cloud users can deploy resources, and there is quite a reserve of capacity in the cloud for scaling and expanding. You will see in our Azure portal in our demonstrations. In the portal is where we can view and create, update, and delete all of our resources, and many of the ways of connecting to Azure exist. We're going to show you the portal, but you can use the command line. There's various deployment tools and all the ways that you can connect. And you're going to see our resources when we create them are going to be in what are called resource groups. Resource groups are lifecycle containers, and we do all of our work inside the resources themselves, either right there in the portal or, as you'll see with AI, often in a studio environment that's designed specifically for that resource. We have already seen Azure Machine Learning and how machine learning forms the foundation of AI's predictive capabilities. Next, we're going to look at Azure AI services in the areas of Azure AI Vision, including the features image analysis and face and optical character recognition. We're going to look at Azure AI Language, including the information extraction, text summarization and classification, question and answering, and conversational language understanding. Azure AI Speech, including text-to-speech and speech-to-text, Azure OpenAI, and Azure AI Search. It's worth spending a little more time examining Azure's AI services as they illustrate a pattern that is common for many AI app scenarios in Azure. To use Azure AI services, you must provision a resource in your Azure subscription. This can be a standalone resource, which is like a service-specific resource. AI Vision is a good example of that, or the general Azure AI Services multi-service account. That resource encapsulates multiple services, and using the standalone is going to give you the ability to save costs and work specifically with that, and has its own security and its own rules. And outside of that, when we're using the larger ones, you'll be able to combine them and get that savings. AI services in a single Azure resource can be centralized for the management. So regardless of the type of resource you use, the client applications will consume that service that it provides by connecting to a REST endpoint. So it's an HTTPS address to which they can submit requests using resource-specific keys for authentication or managed identities. Now let's take a look at Azure AI services in Azure. All right, here we are in the Azure portal. And this is my dashboard view. This is the home view here. You can see I can have my favorites. I can create resources. I can view all of my resources. And we have a sidebar menu, and then we have the front menu. So there's 2 ways you can configure this. If I go into create a resource, I can search for what I want to do. Here's OpenAI. And I can then choose it from the list on the marketplace, and I can find the different resources I want to create. Next up, we have our notifications bell. This is anything that goes on, and while you're working in there, you'll get notifications. And then we also have our settings, and then reporting trouble and feedback are all across the top. I can even open up a command line and interface with my applications directly inside of the Azure portal. Everything is in a resource group, so you can sort by resource group, and you can see that those are lifecycle containers, and we have many resources inside of one, and you can delete them all together if you want to. And that has been a quick tour of the Azure portal, how we create resources and how we delete them. Here we are in Azure AI Studio, and we're going to explore the content safety features. And the content safety works against one of our other items. So here we've connected to our Azure AI multi-services account. And so note before we start, some of this content might be offensive because that's what we're looking for. So this is our text analysis. And so we put in some easy breezy text and we get, this is allowed because it was we know in advance that what this text already has in it. Let's try something that should fail. So this is a violent content. Again, we don't need to read it what it is. We know what the result should be. There it is, it's blocked. But what if we change our tolerance and we are more permissive? So this is going to give you a good idea of what's happening. So here I have a threshold. My threshold is higher. I'm going to be more allowing. We're going to do the violent content again. We're going to run the test, and this time it's allowed. So this is a great way to test your content filters against text you might experience to see what the result would be in your applications or in your AI solution. In this session, we learned how AI models are created with machine learning and neural networks. We discussed the many types of AI models we can include in our solutions and how to access AI in Azure. We're going to take a 10-minute break and come back with session 2, Fundamentals of Computer Vision. Welcome back from the break. This session is about computer vision and how the models are trained and how we're going to use them in our solutions. So our session on computer vision is divided into two parts. It's going to be computer vision concepts, and the second part is computer vision capabilities in Azure. Computer vision concepts cover three main points. So what is Azure AI Vision, the application of Azure AI Vision, and Azure AI services? We start with image processing. So digitized images are made up of pixels. A grayscale image that consists of an array of pixels that are valued between 0 and 255 are white. So color pictures, they're consisting of three arrays. This is our RBG or RGB channels that are going to be red, green, and blue. So that's the difference between the two. Most image processing involves the application of filters, which consists of kernels that define an array of weighted values. So the filter kernel is convolved or passed across and down over the image, and it's going to calculate the values for the new array using the weighted sum of the original pixel values multiplied by the corresponding kernel weights. The new array represents the filtered image, usually with a visual effect. So in this case, a filter named Laplace filter has been used to highlight the edges of the shapes of the original image. And this is what it looks like in a real image. So because the filter is convolved across the image, this kind of image manipulation is often called or referred to as convolutional filtering. There are many other kinds of filters that we can use to create blurring, sharpening, color inversion, and other effects. One of the most common machine learning model architectures for computer vision is the convolutional neural network, or CNN. So the CNNs use filters to extract the numerical feature maps from images. And then we feed those feature map values into the deep learning model to generate the label for prediction. So feed those in as X values. So for example, an image classification scenario, the label represents the main subject of the image. In other words, what is this an image of? You might train a CNN model with the images of different kinds of fruit, such as apple, banana, and orange, so that the label that is predicted is the type of fruit in that given image. So during the training process for a convolution neural network, filter kernels are initially defined using randomly generated weight values. Then, as the process progresses, the model's predictions are evaluated against the known labeled values, and the filter weights are then adjusted to improve the accuracy. Eventually, the trained fruit images classification model uses the filter weights that best extract the features that help identify the different kinds of fruit. The following diagram illustrates how a CNN for an image classification model works. Models with known labels, for example, 0 for apple, 1 banana, 2 or orange, are fed into the network to train the model. One or more layers of filters is used to extract features from each of the images fed through the network. The filter kernel starts with randomly assigned weights and generates an array of numeric values called feature maps. The feature maps are flattened into a single-dimensional array of feature values, and the feature values are then fed into a fully connected neural network. The output layer of the neural network uses a softmax or similar function, and that's going to produce a result that contains a probability value for each possible class. For example, 0.2, 0.5, 0.3. The Microsoft Florence model, which is used for image analysis 4.0 capabilities in the Azure AI Vision, is a multimodal model. So it's trained with huge volumes of captured images from the internet. It includes both language encoder and an image encoder. Florence is an example of a foundation model. In other words, a pre-trained general model on which we can build multiple adaptive models for specialized tasks. For example, you can use Florence as a foundation model for an adaptive model that performs image classification, identifying which category of an image belongs, or object detection, which is locating individual objects within an image, captioning, which is generating appropriate descriptions of an image, or tagging, which is compiling a list of relevant tags for that image. In this next section, we will discuss image analysis with Azure AI Vision Service, detecting faces with face service, and reading text with optical character recognition. This table illustrates the resources for computer vision and how they're divided in Microsoft Azure. The image classification and object detection, optical character recognition, and spatial analysis fall under the vision service. And for the specific models for detecting and recognizing faces, those are in the face service. The Azure AI Vision image analysis service can extract a wide variety of visual features from your images. For example, it can determine whether an image contains adult content. They can find specific brands or objects, or it can find specific objects or text within the image. While the AI Vision service provides some basic face detection and analysis features, the face service offers additional capabilities. All users can use the face service to detect blur, how blurred the face is, in which case it indicates how likely the face is to be the main focus of the image, or exposure, like aspects like underexposed or overexposed, and it's going to apply to the face and the image and not the overall image exposure. Whether the person is wearing glasses, the head pose, the face's orientation in a 3D space, and even noise, which refers to visual noise in the image. So if you have taken a photo with a high gain setting for darker situations, you might notice noise in the image, which is like grains or dots. Occlusions are objects blocking the face in the image. So it's important to note that anyone can use the face service for that. We can detect the location of the faces of an image. We can determine if the face is wearing glasses, determine if there's the occlusion, blur, noise, over, underexposure, and it can also return the head coordinates and the pose. The model makes no prediction about the faces it detects, allowing responsible use for a wide audience. However, to support Microsoft's responsible AI principles, facial recognition is under limited access policy. And the reason is it has the ability to compare faces for similarity and the ability to identify named individuals in an image. So we've discussed the computer vision service and its use in image analysis, but it also provides optical character recognition, or OCR, capabilities that can detect and extract text from images. So the service is provided in the Read Application Programming Interface, or API, and software developers can use that to extract both printed and handwritten text from images, from immediate reading of small amounts of text in images to asynchronous text extraction from large documents. We have 3 demonstrations to cover now, and they are the analysis of images in Vision Studio. And in this demo, you're going to see the AI Vision service and analyze images, also detect faces in Vision Studio. We're going to look at the faces detection capabilities of Azure AI Face Service. And then in Vision Studio, we're going to see that AI Vision's optical character recognition capabilities in action. So let's go to those now. Here we are in Azure AI Studio, and we're going to work with our images. So we're going to scroll down and we're going to find our vision and document section, and we're going to move to image analysis. So we're going to do common object detection first. And I'm going to go ahead and connect to my hub, and then we're going to choose an image. So here we have, here we go, footwear, person. And you can see the bounding box showing up on there. Let's try another one. Bicycle, it has 3, and then when we change our threshold value, you see it went for the bigger objects. Let's take a look at image captioning. And here we just want a caption for the image. This is going to give us a man holding a surfboard. That's great. Let's go back. Let's do dense captioning. So dense captioning is going to give us a lot more from the image. So here we're going to see a close-up of a ball of pasta, a close-up of noodles, a blurry image of food, that type of thing. And it gives us the bounding boxes again. Let's try another one. This one is a man driving a tractor, the blue sky above a hill. So you can see how the dense captioning gives us much more information. Now we have image retrieval. So metadata about our images will help us find them in large pools of storage, right? So here I want sunset in the mountains from a list of 200 and some pictures, and I get 10 back, and I can be even more filtering, and I get like 6 back. Let's try that again. Here, let's go ahead and choose students using laptops, and let's trim that down to a much more usable number of images. There we go. All right, common tags. Look at all the tags we're getting, and we get a confidence level with them so we can sort those out in our applications. All right, text from images. Here you see we get the text and the bounding box for where it is on the item, and so the key value pairs are there, and those were included in the document. Here's another one with the credit card. We get the different parts of the credit card number, and then the valid dates and the name and all of that. Let's try the bicycle one. There we go. The life is like riding a bicycle. You see we get all of the text that's coming out of there. And this has been, let's do nutrition facts too before we go. Let's go look at this. This might be a good usage of that. We have, you see how it comes back, saturated fat or trans fats or calories, all of that works together. And then detect faces. So this is, we're not learning anything about the faces, we're just detecting them. And this is gonna tell us if they're wearing a mask or not. You see there's face 1, face 2. Again, there's face 1 because there's only one person, and this one has a mask, you can see. And that's been a quick tour of image analysis in Azure AI Studio. So we've looked at the computer vision in Azure, and we discussed the various ways we can gain insights from images. From knowing if an image is a banana or not, or if there is a banana in the image somewhere, or to pulling text from an image or removing a background. We finished with understanding facial recognition and the difference between detecting if a face is in an image and gaining insight about the face itself. This concludes our session. We're going to take another 10-minute break and come back with session 3, Fundamentals of Natural Language Processing. I'll see you back in a bit. Welcome back from the break. This next section is about natural language processing and how the models are trained and how we're going to use them in our solutions. So let's get started. The session is in two parts. The first part is natural language processing concepts, and the second part is natural language processing capabilities in Azure. So what is natural language processing? We're going to answer that. What is conversational AI? We're going to answer that. And then we're going to talk about natural language processing and conversational AI in Azure. So natural language processing, or NLP, it's an area of AI that deals with making sense of written and spoken language. So creating an NLP solution starts with a large volume of text, which is then pre-processed to prepare it for modeling. There are many pre-processing techniques that can be applied to text, including stop word removal, eliminating common words with little semantic value like or the, stemming or lemmatization, which is coalescing words with the same root as a single word. So for example, universe and universal might be represented as universe without the E, so UNIVERS. And there are other techniques. So many of these approaches were extensively used in statistical modeling techniques that relied on counting the frequency of words in text to derive meaning, but they're not so important in the modern deep learning techniques. One thing that is commonly done is to tokenize the words, representing each distinct word or phrase with a unique numeric identifier. The set of tokens represents the vocabulary for a language model. The data is then used to train the model. Depending on the type of task you want to accomplish, the details of the model will vary. For example, you might use a fully connected neural network to train a classification model for sentiment analysis, and that's going to be predicting whether the body of the text is positive or negative or neutral. You might even use a more sophisticated network to train a model that encodes a language tokens as vectors, and that encapsulates the semantic relationships between the words. So what that means is a vector is a number, and a vector is a place on a chart. So that when they show up close to each other, then they are semantically similar. So a gardener and a farmer are going to show up as vectors very close to each other, but a gardener and a computer scientist might be further apart. So common tasks that language models can support include text analysis. Often you need to analyze a text document to extract key phrases or identify entities that it mentions, such as dates, places, or people. For example, a large company might use AI to analyze industry magazine articles to find the articles that mention their products or executives, or to determine the main subject of each article. Opinion mining and sentiment analysis is a common form of text analysis. It's going to calculate a score indicating how positive or negative the text is. For example, a retailer might analyze reviews from customers to determine which ones are positive and which ones are negative or neutral, and analyze the text to uncover key drivers of the sentiment. Machine translation, international and cross-cultural collaboration, right, is often a key to our success. So translation is going to require the ability to eliminate the language barriers, and AI can be used to automate the translation of written and spoken language. So for example, an inbox add-in might be used to automatically translate incoming or outgoing emails, or a conference call presentation system might provide simultaneous transcript of the speaker's words in multiple languages. You might want to take a large volume of text and generate a summary of its key points. Conversational AI is a form of AI in which an AI agent engages in dialogue with a human user. Commonly, this form of application is described as a bot or chatbot. To support these kinds of interactions, a language model must be developed that enables the AI agent to interpret the incoming request. It has to determine the semantic meaning or intent of the request and then formulate an appropriate response. The language models in Azure are language detection, key phrase extraction, named entity detection, sentiment analysis and opinion mining, personal information detection, summarization, question answering, conversational language understanding, and the speech models are text-to-speech, speech-to-text, speech translation, speaker identification, language identification, and the translator services include text translations, document translations, and custom translations. Let's talk about the natural language service in Azure. Azure AI Language Service provides pre-trained and customizable deep learning models to analyze text. These models use tokens and embeddings to turn words into numerical representations. Deep learning models perform calculations on these numerical representations to provide responses returned in natural language. Text analysis encompasses many capabilities, including identifying the predominant language of the text, identifying the sentiment of the text, identifying the key phrases, and identifying entities. The slide shows examples of using the sentence, "I had a wonderful vacation in France." The predominant language is English. The sentiment is positive. The key phrases are wonderful vacation, and the entity is France. Let's look at analyzing text with Language Studio. Here we are in the Azure AI Studio. We're going to look at analyzing some text. So we want to get some sentiment from here. And what we have are some pre-built messages that we can test. So let's go ahead and run these. Now, here's my sentiment. Mixed sentiment for the sentence of my product review. Let's try the service review. All right, we'll run that. Again, mixed sentiment. And it's telling me at the bottom, if you notice these come up, it's telling me which parts of the sentence are giving me the reaction. So there we have technically recharged. That's going to be positive. Okay, and it's giving us the confidence level as well as we scroll down and look at those. This one's negative. We have sentence 1 and sentence 2. These both turned out to be negative, and it tells us exactly where it came up to that. So this is sentiment analysis. We send our short text to that, and that's been a quick tour of how we analyze text in Azure AI Studio. You can use the language service to define a knowledge base of question and answer pairs. You can create the knowledge base by entering questions and answers, or you can import an existing fact page or frequently asked questions page. You can also augment your questions and answers with built-in chit-chat sources that include common conversational exchanges. After creating the knowledge base, you train a model based on the question and answer data and publish it as a service. Client applications, particularly chatbots, can then use the knowledge base to determine appropriate responses to the user input. Azure Bot Service provides a platform for creating, deploying, and managing bots. With the Azure Bot Service, developers can use Microsoft Bot Framework SDK or Software Development Kit to develop bots and easily deploy and manage them in Azure. By using the Azure Bot Service, you can easily integrate your bot with a language service for language understanding or question answering, and connect your bot to multiple channels such as web chat, email, Microsoft Teams, and other places. In this demo, you'll see Azure AI Language's question answering capabilities in action. All right, here we are in the Language Studio, and we're going to do a custom question project. So we're going to go ahead and create our project. And what I'm going to do is this is going to be a travel knowledge base, and we're going to use a travel FAQ. So we're going to give it a little bit of a list. We're going to do this in English, and we're going to go ahead and create the project. So I have a URL that has all of the information about my travel. So I'm going to go ahead and paste this in here. So this is my FAQ document. It's going to retrieve that from my web page, and it's going to pull in all of the facts, and it's going to map them to questions and answers. But let's go ahead and add our own custom one here so we can test it. When I type in hello, I want the answer to be hi. Okay, so now we're going to go ahead and save those changes. Now let's go test it. So the training on this happens automatically when you're doing the saving. So we're going to do include short response because we want to see exactly what we're going to get back here. I did hello, I get hi back. Let's try something from the left. Let's see here, what services do we provide? It's going to tell us a little bit about it. Now we can say we want to book a flight, and we should see what our potential answers here. There's a short answer and a long answer. So we can follow that up. All right, should we try some more? Let's see here. What about canceling? Let's just make sure these are all working. How can I cancel my flight? There we go. All right. So you can see I got both answers there. So now the next step is I've got to do something with this model so I can test it. So what I'm going to do next, we'll go ahead and close out of that, and we're going to deploy our knowledge base. So yes, I want to deploy this. What this does is it makes it something that I can use then from an application. So I'm going to go ahead and deploy it. And now once I've done that, I'm going to create a bot. So this is going to take me over to the Azure portal. I'm going to create a new bot. And we're just going to give it a resource group here real quick, bot.rg. It's given us a name that we can use. And we'll go through and make sure everything is appropriate. And then we have to put the language resource key in. So we can find that in our language resource. We can go ahead and grab that key and paste that in. And then I can go ahead and do my deployment. Now, once my deployment is done, you can see my bot showed up and I have a test in web I can do. Once I open that up, I can say, well, let's see here. I can say hello. Okay, it's queuing up. It said hello and welcome. That's how it defaults. Let's try hello again. There we go. Hi is the answer. And then I want to cancel my reservation. And it's going to go ahead and tell me a little bit about reservations. I want to book a flight. Let's see what it says. All right. So it looks like it's working in our app. And now we can go ahead and deploy this application in our web apps or in Teams and use it all around. That's been a quick tour of creating a Q&A knowledge base and a bot. The language service enables you to train a language model that can interpret natural language commands. The language model consists of 3 primary components. These components are utterances and phrases that the user is going to might say or type in something like switch the light on. Entities, which are specific items that are referenced for an utterance, in this case like a device, or a language model for a home automation application might recognize light or fan. An intent. What does the user want to do? It identifies the desired action for the utterance. So switching on a light or turning off a lamp. In this demo, you'll see conversational language understanding with Language Studio in action. So here we are in the Language Studio. And what we want to do is we're going to understand conversational language. We're going to use the conversational language understanding, and we're going to create a project. So we create a new project. We'll give this one a name. This one is Home Automation, and we'll go ahead and create that. Just take a few seconds. Now, there's nothing in here. What we want to do is go to our schema definition and add an intent. This intent is going to be switch on. So our application will then know switch on once we train it to understand what the inputs are. So inputs here are called utterances. So let's map switch on to some utterances. Switch on the fan. Let's add a few more. So we're going to go ahead and put the fan on. We're going to iterate over this, put the light on. We're going to have a couple of devices here. Yep, switch on the light. All right, so we probably, turn the fan on. A couple different ways of saying the same things. The next thing we need to do is add an entity. So the entities are the lights or the fans or the oven or the television. And what we're doing is we're saying, this is a device, and now we're going to map our utterance to the device. All right, so we keep choosing device, fan, light, etc. Now, it's not going to matter what we choose because it's going to learn on this what a device is, and it's going to be able to map that device. And then what we'll get back is the result of switch on, and then we'll also get that entity so we know which thing to switch on. If you're going to switch it on, you got to switch it off. So let's go ahead and make another schema definition of an intent for switch off. We're going to do the same thing here. So go a little bit quicker. We're going to map this one to switch off. Turn the light off. Should we have switch the light off? And again, every time you type something in, you just hit enter, and it's going to go ahead and save that for you down below. Put the fan on, turn the fan on or off, etc. So we don't have to add all of the devices that we have. We just have to have a couple in here and several examples. We'll go ahead and map this to device as well. So now we can get 2 intents back, either switch on or switch off, and then the name of the device. And our application will then be able to turn on and turn off the different devices. Let's take a look at how this looks. So what we need to do, we're going to create a training job. And once that training job is done, we're going to then deploy the model. So we're going to do an app, or we're going to do a deployment of it. So this is our deployment name. So I'm using the same names here. So this is the deployment. We'll go ahead and map it to the model. So now we're deploying a very specific model. And then once that's deployed, we're going to go ahead and then test the deployment. So there's our deployment. And now I can say turn on the light. We can select to run it. And there you see our top intent is switch on and the device is light. I can do switch off the fan. Again, top should be switch off and the fan. Let's try something different. Let's do flip on the oven. Okay, top intent switch on. Device is the oven, which we never trained it for. Let's do the TV. All right, as you can see, it's learned how to determine what devices are and what the intents are, and that's been a quick tour of language understanding. The speech service provides a speech-to-text API that you can use to implement text recognition functionality. The service supports text transcription in more than 60 languages. Here on the slide, you see the bubble represents the spoken language, and then the box of text represents what was said. Conversely, the text-to-speech API can synthesize audible speech from text with the option to specify regionally appropriate voices for human-like pronunciation. As shown on the slide, we see the text, and then we see the bubble representing the audible sound that comes out. In this demo, you're going to see Azure AI's speech capabilities in action. Now let's take a look at speech. Again, we're in the Azure AI Studios. We go to speech. We want to do real-time speech to text. And we're going to try an example out real quick. So what I need to do is here I have a file on my computer. I'm going to drag it over. And it's going to start analyzing it right away, even before I play it. But let's go ahead and play this audio so we can hear what it sounds like.
AI enables us to build amazing software that can improve healthcare, enable people to overcome physical disadvantages, empower smart infrastructure, create incredible entertainment experiences, and even save the planet.
Excellent. And you can then extract the text. We can also look at the JSON and we can see what that looks like. And that is a quick tour of speech services, speech to text. In this session, we discussed natural language models and how to use them in our solutions. This concludes part 1 of this course. Thank you for your attendance so far, and we look forward to seeing you next time for part 2 of AI Fundamentals.